Hey guys, in this video I'll talk about the second derivative test, which allows us to analyze functions and see which intervals they're concave up and concave down in. So previously we talked about the first derivative test, which told us where the function was increasing and where it was decreasing. Now this test tells us which intervals the function's slope is increasing or decreasing at. So previously we saw if the function itself was increasing or decreasing, and now we're seeing if the slope's getting bigger and bigger or smaller and smaller. So similar to the first derivative test, we start off by finding where the second derivative of the function is 0. And once we do this, we can split up f of x into those intervals. So let's say a and b were the two areas where the second derivative was 0. Then we can mark these on the line and split this graph into those intervals. So now we want to test each interval and see exactly if it's concave up or concave down in those intervals. So let's say we tested a point less than a, and we found that the second derivative was positive. You can mark that and keep going with each interval. And now that we know what the number is, what the second derivative actually is, or if it's positive or negative, we can see what this means for the actual graph. So a positive second derivative means that the slope is increasing, which means it has a concave up shape. So it looks like a part of an upward facing parabola. Keep in mind, this doesn't mean the function's increasing, because that's what we found out in the first derivative test. This just tells us if the slope is increasing or decreasing. So if the function's decreasing and it's concave up, it might look something like this half of the parabola. And then if the slope is positive, if the function's increasing and it's concave up, it might look something like this part of the parabola. So if we continue with each of the intervals, we can see that a negative second derivative translates to a concave down shape, and a positive second derivative translates to a concave up shape. So now let's look at an actual function and see how we can apply this. Let's say we're given a function f of x equals 2x cubed plus 3x squared minus 36x. We'll find the first derivative using the power rule, and find the derivative of this function using the power rule once again, and we see that the second derivative of f of x is 12x plus 6. Now using this, we can see that f double prime of x is 0 when x is negative 1/2. We can mark that in our line, and now we split our function into two intervals. So now let's test a point less than negative 1/2. If we choose a point like negative 1, we see the second derivative is negative. So we mark that. And if we choose a point greater than negative 1/2, let's say 0, we see the second derivative is positive. We mark that as well. So now we see that for every x point less than negative 1/2, the second derivative of this function is negative. And for every point where x is greater than negative 1/2, the second derivative is positive. Now we can see what this means for the actual graph. If the second derivative is negative, the function has a concave down shape. So it looks like a part of a downward facing parabola. And for every point where x is greater than negative 1/2, it's concave up, meaning it looks like a part of the upward facing parabola. So using this test and the first derivative test, we can see where the function is increasing, where the function is decreasing, where it's concave up, and when it's concave down. And using all this information, we can sketch a graph. So we can translate these numbers and variables into a picture and make it easier for us to visualize.